In this problem, he is asking to find the Laplace transform defined by f of t is equals to a by t naught for 0 less than t less than t naught and 0 for other t less than t naught, t greater than t naught. Now we have wrote a by t naught for 0 to t naught. Then he is dividing this f of t into two parts. f1 of t is a by t naught of a constant magnitude and f2 of t is minus a by t naught from t naught to infinite time, it is constant. By adding 2 you will get a by t naught into u of t plus minus a by t naught into u of t minus t naught. Now if you convert it into Laplace transform, you will get it as f of s is equals to a by st naught as common into 1 minus e power minus st naught. In this problem, he is asking to find the inverse Laplace transform. In the given form g of s, numerator is greater than denominator. Always keep in mind the order of the denominator must be greater than the order of the numerator. But in this question, order of the numerator is greater than the denominator. So we must do the division. So write numerator as dividend and divide it with divisor s square plus 3s plus 3 and you will get quotient as s plus 2 and remainder as s plus 1. So we can write in this form quotient plus remainder by divisor. So by making this into partial fractions, you will get s plus 2 plus 2 by s plus 1 minus 1 by s plus 2. So in this problem, from this problem you can understand that numerator order of the numerator should be less than the order of the denominator. In this problem, he is asking to find output voltage by input voltage. By seeing the op amp, the input is given to the positive terminal. So it is a non-inverting amplifier. And negative terminal is connected to Z1 and Z2, where Z1 is resistance connected in series with capacitor, where Z2 is resistance connected in parallel with capacitor, where Z2 is the feedback elements. So it is a non-inverting amplifier, op amp. So there is a direct formula to find such type of op amp circuits. To find the transfer function output voltage by input voltage, there is a direct formula, that is Z1 of s plus feedback element Z2 of s divided by Z1 of s. So output voltage by input voltage is equals to Z1 of s plus Z2 of s divided by Z1 of s. In this problem, he is saying to find the output voltage by input voltage. So here we are using two op amps and there is a bridge resistance between the two op amps, that is R3. Here for first op amp, R1 is the input resistance and R2 is the feedback resistance, and for second op amp, R3 is the input resistance and R4 is the feedback resistance. So this type of op amps are known as proportional controller. To find the transfer function, there is a formula, that is product of the feedback elements divided by product of the input resistance. As the input is given to the negative terminal, it is inverting op amp. So to find the transfer function for the inverting op amp, there is a formula, that is minus feedback resistance by input resistance. So directly we can write such type of circuits as proportional controllers and we can solve the problem. In this circuit, it is same as the proportional controller, but the first op amp feedback resistance is replaced by a capacitor C2 and it is known as an integral controller. So to find the transfer function of an integral controller, it is same as product of the feedback resistance divided by R3 C2 R1, that is R4 into 1 by S by R3 C2 R1. In this circuit, it consists of a capacitor and resistance in parallel, then another two op amps are connected, same as a proportional controller. So in this Z1 is taken as the parallel circuit of C1 and R1. To find the transfer function, we will use the formula to find the output voltage by input voltage of a inverting amplifier, that is minus RF divided by R1. So output voltage by input voltage we have done as minus R4 by R3 into minus Z2 by Z1. Here Z2 is R2 and Z1 is R1 parallel with C1. He is coming from output voltage to input voltage. So overall you will get it as product of the feedback resistance by divided by product of the input resistance, same as proportional controller, plus, and this is the R4 R2 by R3 R1 into R1 C1 into S. This is same as proportional plus derivative controller. In this circuit, he is showing about the proportional plus integral controller. In proportional plus integral controller, the feedback resistance is replaced with a series circuit of resistance and capacitor, and the input is given to the negative terminal, so it is a inverting op amp. So you will get output voltage by input voltage formula as minus RF divided by R1. By solving the above circuit, you will get it as a proportional plus integral controller, where proportional control is Kp and integral control is Ki by S. So Kp you know it as R4 R2 by R3 R1, and Ki is integral controller, that is R4 by remaining all R3 R1 and C2 into 1 by S. In this circuit, it is showing the total proportional plus integral plus derivative controller. First, input capacitor and resistor C1 and R1 in parallel, that represents the derivative controller. Next, feedback path R2 C2 are in series as a feedback elements, they represent the integral controller, and this remaining op amp R4 and R3 represents the proportional controller. So proportional controller plus integral controller plus derivative controller, you can write it as Kp plus Ki by S plus Kds, where Kp you know, you will write it as R4 by R3 into R1 into C2 into R1 C1 plus R2 C2 plus so on. So you will write overall equation as like this. In this problem, he is asking to find the time constant. The given system 5 by S plus 5, it is a first order system. So rise time for a first order system is 2.2 into time constant, where settling time is equals to 4 time constant. Where time constant from the 5 by S plus 5, time constant you can write it as 1 by 5, that is 0.2 seconds. If peak overshoot is 10%, then damping ratio is 0.591, which is approximately equals to 0.6. If percentage of peak overshoot is 20%, then damping ratio is 0.456. If percentage of peak overshoot is 25.4, then damping ratio is 0.4. If percentage of peak overshoot is 30%, then damping ratio is 0.358. Percentage of peak overshoot and damping ratio are inversely proportional. If system has lower damping ratio, then it has peak overshoot high. In this problem, he is asking to find the steady state error due to phi into u of t, phi t into u of t, and phi t square into u of t. Here E of S is specified after the summer. So this E of S is specified after the summer. This is summation. Summer. This is the actuating error. If E of S is present, there will be no problem. Go same as for the procedure as take open loop transfer function g of s h of s, then substitute the values same to find kp, limit s tends to 0 g of s, for kv limit s tends to 0 s into g of s, for kv ka limit s tends to 0 s square into g of s, and find the steady state error. And this is the case 2. If the question consists of overall transfer function, closed loop transfer function, now convert this closed loop transfer function into open loop transfer function. We can convert this closed loop transfer function into open loop transfer function by making numerator by numerator, denominator minus numerator. You will get g of s. After getting g of s, same as the procedure, you can find kp, kv, ka. So if summer is not present, E of S is not present after summer, then you will do this procedure. In case if he has given G of S and H of S, and if he asks to find the steady state error, error is not shown after the summer, hence we can assume it as output summer. Now consider H of S. Limit S tends to 0, H of S. Limit S tends to 0. Take this S outside and write 10 by S plus 5. You will get, and substitute in that bracket S is equals to 0. You will get S into 2. The 2 constant is nothing but the KH. Now write the overall transfer function, closed loop transfer function, G of S by 1 plus G of S H of S. This is the second step. And the third step, you will find the steady state error. There is a formula to find the steady state error, that is limit S tends to 0, S into R of S divided by S into KH into 1 minus S into KH into closed loop transfer function. In this we have given R of S is equals to 1. Now we will substitute the values. Steady state error is equals to limit S tends to 0, S into 1 by S, where R of S is 1 by S, divided by S into KH, where KH is equals to 2, 1 minus 2 represents KH, and 2S into overall transfer function is S plus 5 by S square into S plus 2, S plus 5 plus 10S. Now limit S tends to 0, SS get cancelled and 1 by 2S. Now by solving this problem, you will get S cube plus 7S square plus 85 divided by S cube plus 7S square plus 10S plus 10. By substituting S is equals to 0, you will get 8 by 2 into 10. That is equals to 0.4. Okay, for the system shown in figure, K1 and K2 are given. Unit step functions are for input R of S and disturbance. He is asking to find the steady state error. In this problem, first you must assume that R of S is equals to 0 and then find d of c of s by d of s, and next you must assume d of s as 0 and find c of s by r of s. So steady state error is equals to 1 minus, first term is he assumed d of s is 0, so s into r of s into g1 g2 by 1 plus g1 g2 h. In second term he assumed r of s is 0, limit s tends to 0, s into d of s into g2 of s by 1 plus g1 g2. By substituting these values, 1 minus d of s 0 minus r of s 0, you will get 1.9 by 12. For a type 1 second order control system, when there is an increase of 25% in its natural frequency, then steady state error due to ramp input. Always keep in mind, steady state error is inversely proportional to omega n. As steady state second order system which has a increase of natural frequency of 25%, steady state error will reduce by 20%.